Hello, welcome to the Wide Bandgap Conference Power Integrations presentation. My name is Mike Matthews. I'm the VP of Product Development at Power Integrations, and I'm here today to talk to you about a new application of our PowiGaN gallium nitride transistor technology in a new and innovative product for reducing the size of AC-DC wall adapters. Now, PowiGaN is not new. We've been shipping it as part of a product called InnoSwitch 3 for some time now. InnoSwitch 3 is a flyback power supply converter chip. The PowiGaN is positioned here on the primary side, and on the secondary side is a controller which controls the switching of the synchronous rectification MOSFET here, but also controls the primary side PowiGaN switch, and it does that through means of a flux link communication channel between the secondary and the primary of the power supply across the isolation barrier. This is a magneto-inductive coupling that's built within the package of the chip. As I mentioned, we've been shipping for some time. We actually have about 80 customers in production and more than a dozen different applications. Many of them are wall adapters for smartphones and tablets, but increasingly we're seeing applications for products such as smart speakers, domestic appliances, AC, air conditioning, in-wall USB outlets, ballast for lighting. And actually the first application of PowiGaN in a power supply was in a TV power supply. But as I mentioned, I'm here today to talk about a new product, and I'll go back to the schematic just to illustrate what that is and what our focus is for today's discussion. And the focus is specifically on a component called the bulk capacitor. The bulk capacitor is an energy storage element on the input of the power supply, and its job is to filter the ripple from the AC line so that the downstream power converter, in this case a flyback converter, can operate efficiently. Now the challenge with the bulk capacitor is that the amount of capacitance you need is governed by the minimum input voltage to the power supply, but of course the voltage rating of that capacitor has to be designed to cope with the maximum input voltage of the power supply. And many of these power supplies are wide range input. 90 volts to 265 volts AC is a typical range. So the amount of capacitance you need is governed by the 90 volt input, but of course they have to be rated for the maximum input voltage, which when rectified is about 400 volts, just under 400 volts. So typically these bulk capacitors are 400 volt rated, but the capacitance, the number of microfarads, is designed to cope with the lowest input voltage. And the reason for that is that the energy on the capacitor is 1/2 CV squared. And so for a certain amount of energy, when the voltage is low, of course the capacitance has to be higher. So it's that combination between capacitance for low voltage, but the voltage rating for the highest input voltage, which is what makes this bulk capacitor so large. In fact, if you open up an adapter, you'll see that the bulk capacitor is typically about 25% of the overall volume. It's actually very similar in volume to the main power transformer shown here. So the other question might be, well, why even bother trying to reduce the size of these wall adapters? And there's a few reasons. One is that batteries inside these mobile products are getting bigger. Consumers are requesting faster charge times, so obviously that all demands higher power. The charging control schemes are becoming more and more sophisticated, USB PD for example, and so the challenge is to fit more power and more complexity into a smaller size. Now there are some other ways of reducing size of the power supply. One is to reduce component count. That's something that we've spent a lot of time doing at Power Integrations, as have others. The other technique traditionally used is increasing the switching frequency of the power supply, and that reduces the size of the power transformer that I mentioned a few minutes ago. And that's certainly a very legitimate way of reducing size. It does very often, though, add to other complexities. The construction of the transformer, the losses in the transformer tend to go up, but also the size of the input EMI filter tends to increase. And so there's a trade-off between reducing the size of the transformer whilst increasing the EMI filter size. So we decided we wanted to come up with something a little bit different, something that's efficient, simple, and of course cost-effective. So let me introduce our new IC. It's called Minicap. It stands for Miniaturization of the Electrolytic Capacitor on the input to the power supply. Now, the idea is actually very, very simple. And like many simple ideas, it leads to a very elegant and simple solution. And it's simply this. We split the input capacitor into two parts. One is a high voltage capacitor designed for operation when the input voltage to the power supply is high. And then a second lower voltage capacitor, but with much higher capacitance in terms of microfarads, which is switched into the circuit when it's needed at low input voltage. And it's the job of the Minicap to decide the charging and also when to switch that low voltage capacitor into the circuit. And the Minicap therefore manages both the charging and the discharging of this capacitor, and also protects it from the higher voltages when the input voltage is high. Now, that combination of a small high voltage capacitor and a much larger low voltage capacitor reduces the overall size of the bulk capacitor on the input by about 50%. What may be surprising is that itself can lead to almost 40% reduction in the overall size of the power supply. And the reason is the bulk capacitor is normally such a bulky component that it makes the layout very inefficient. There is wasted space around the capacitor. And I'll show you a couple of examples in a moment where this sort of size saving can be achieved. What is a little bit less obvious on first glance is that this introduction of the Minicap and the isolation of this 160 volt low voltage capacitor from the circuit means that the inrush current that's flowing into the power supply when you first plug it into the wall is much, much reduced. And that eliminates the need for a component called an NTC, which is normally positioned here on the input line. And the job of that NTC is to control the inrush current so that you don't get excessive arcing. Anyone who's plugged in an adapter to the wall and you see arcing as you do that, it's because of inrush current. And NTCs are there to control that inrush current to a safe level. With Minicap, it's entirely unnecessary to have that component at all. So that saves about 1% efficiency in the power supply overall. So it's a very simple idea, and the immediate question is, well, then why wouldn't someone have done this before? And that's where the PowiGaN comes in, and it has three specific attributes which make it very well suited to this application. The first may not be very surprising, is low conduction loss. Gallium nitride, of course, is a very low RDS-on, a low specific RDS-on technology. The other one is that the PowiGaN is very tolerant to high line voltages, surges and swells, fast transients, and so on. It's a 750 volt rated device, so very robust for this type of application. But the third attribute, which is critically important, is that the PowiGaN has a very low off-state leakage current. And when you position a switch in series with a capacitor of this type, you must make sure that there's very, very low leakage. Otherwise, there's a danger of overcharging that capacitor, and that impacts the reliability of the capacitor if it ever comes close to its rated voltage. So it's very important that the switch in series with that low voltage capacitor is very low leakage. As I mentioned a moment ago, it's designed for wide range input applications, 90 volts to 265, but also equally well suited for 90 to 350 or even 400 volt AC input range that we see in some applications in places like India, for example. And under all of those conditions, the Minicap manages the introduction of that low voltage capacitor so that there's no effect on the output ripple of the power supply. And then finally, of course, to save size, it has to be very, very simple, very few external components. And we actually have only 3 external components necessary, and it interfaces directly to the InnoSwitch family of products downstream. Although it looks like a very, very simple concept, the controller that drives the PowiGaN is one of the most sophisticated controllers we've ever made. It has to be very, very precise, very fast protection for surges, inrush, and so on. So it's a very sophisticated controller, even though it's a very simple end application. So here's one example, a 65 watt power supply. You can see a credit card behind just to show you the size, a little bit smaller than a credit card, very, very low profile. There's the InnoSwitch, there's the Minicap, and here are the 2 bulk caps. And you can see just from this layout that the only reason that it can fit into this very low profile is because you have this very slim 100 microfarad 160 volt cap. If that capacitor had to be rated for 400 volts, as it would normally be, you would either need about 3 of these, or it would be a larger diameter capacitor, which would have a disproportionate effect on the overall outside enclosure. And obviously, if you had 3 of these, it would be a much, much bigger enclosure as well. An even more dense design is this one. This is an ultra slim, again, USB PD power supply with a Type-C output. In this case, it's 8 millimeters top to bottom profile on the the side view of the PCB. And this one again illustrates the power of this concept. Here are 2 10 microfarad 400 volt caps and 2 33 microfarad 160 volt caps. So you can imagine if all of these capacitors had to be the 400 volt capacitors normally used, you would need 7 or 8 of these 10 microfarad capacitors to get anywhere close to the same amount of energy storage. And you can see that, of course, then would be totally unmanageable in a small layout of this type. This design is one where you would have the folding AC prongs coming into this region, and that would fold out and plug into the wall. So this is an actual plug into the wall power supply as well. And you can see next to a US 1 cent coin just how small this is. It's really very, very difficult to imagine how to do this without the reduction of the size of the input bulk cap. So in summary, the gallium nitride technology is clearly enabling all types of new innovations like the Minicap. Even for the existing products that I mentioned at the beginning, the InnoSwitch family, we're expecting to ship around 12 million PowiGaN transistors this year, by the end of the year. And then in addition to that, now we add the Minicap family, which reduces the size of the power supply with very much very simple application. It's less expensive and simpler than the high frequency solutions. It's made possible specifically because of the GaN technology, and in particular the low RDS(on) leakage and high surge capability. And we're actually already in production. We're shipping already to the first customers. And then just finally, the table at the bottom here just shows for the various types of applications what we see as the main attributes of the GaN technology that make it attractive to customers. Of course, high efficiency goes without saying. All customers looking for that now. Small size, in particular for wall chargers and lighting ballasts. No heatsink has become a very popular requirement by customers trying to reduce the weight and the size of power supplies of this type. Interestingly, we see GaN as a way of increasing reliability. We find that the high voltage capability against surges and swells and fast transients is a way of increasing the reliability of the power supply. And then finally, as I mentioned, the very low leakage of the PowiGaN technology makes it extremely good at lowering standby consumption and no load. So with that, I will finish, and I'll be glad to take any questions that you may have, and I thank you for your attention.